Hi, everyone. I'm Yangyang, a graduate student at Princeton. First of all, I'd like to thank the organizers for having me here. It's a pleasure to give a talk in the first Geometric Analysis Festival virtually. Today, I would like to talk about generic regularity of minimal hypersurfaces in dimension 8. This is a joint work with Zhihang, who's also a graduate student at Princeton. Here is the outline. I'll start with the background on minimal hypersurfaces. Then I'll move to existence of singularities. I'll talk about perturbation of singularities and generic regularity of minimal hypersurfaces. This is the main result of our work. Finally, I'll talk about some key ingredients in the proof for the generic regularity. So let's start with the preliminaries. Here's our setup. Let's consider M to be an n+1 dimensional closed Riemannian manifold, and G is the Riemannian metric. Sigma here is an embedded closed hypersurface. We say that sigma is a minimal hypersurface if it's a critical point of the area functional. Here, Hn is the n-dimensional Hausdorff measure. Another characterization is that the mean curvature of sigma is 0 everywhere. Then for minimal hypersurface sigma n, we can consider a so-called Jacobi operator L sub sigma, which is associated to the second variation. Its explicit formula could be written as the following, which is the minus Laplacian plus some terms related to the second fundamental form and also the Ricci part. And the vector v here is the unit normal along sigma. We can define the Morse index of sigma to be the dimension of the maximal subspace where L sub sigma is negatively finite. Intuitively, this denotes the number of directions that you can decrease the area of sigma. In particular, we say that sigma is stable if the index, the Morse index of sigma itself is 0. So in fact, if sigma is integral currents or integral variables, then everything defined above could be generalized. This is just for experts on GMT. And a natural question is that whether we can find a minimal hypersurface in a given Riemannian manifold. And the answer is yes. So let's take a look at the first one. The first result in around 60s and 70s by DiGiorgi, Fedor Fleming, and James Simons, who showed that if the n-dimensional homology class of the ambient manifold is non-trivial, then there exists a minimal hypersurface sigma n, such that the dimension of the singular set is no greater than n-7. In other words, the codimension of the singular set is at least 7. So here let's define the singular set. First of all, let's start with the regular part. We say that X inside the regular part of sigma if X is inside the closure of sigma. And moreover, we can find the neighborhood U of X inside the ambient manifold such that sigma bar intersect with U is a smooth hypersurface. And for the rest of the part, the closure of sigma minus the regular part is defined to be the singular set of sigma. And without loss of generality, we can always assume that sigma is identical to its regular part. So as you can see here in the picture, if we have a cone, then the single set is simply the vertex here, and everything else should be the regular part of this hypersurface. So how the toy model of this theorem is the following. If I have a, say, let's consider a torus, then we can minimize the volume HN among all the meridians, right? So we can have infinitely many different meridians, but if we try to minimize it, then by geometric measure theory, we can say that we can show that there exists an area minimizer denoted by sigma n. Using dimension reduction by Federer, we can even show that sigma n is smooth outside a small set. In other words, as I mentioned before, the dimension of the single set should be at most n-7. So the existence holds if the n-dimensional homology group is non-trivial. Then what about the general case? Even if the n-dimensional homology group is trivial, and this was proved by Amgren Peace, and then using some deep regularity theory by Shen and Simon in 1981. So the main theorem says that for any given closed Riemannian manifold, we can still have a minimal hypersurface with the same regularity as above. This is the so-called Amgren-Peace min-max theory. The toy model should be as follows. We can consider the set of P of some maps. We call it sweepouts, which is a map phi from the interval to the cycle space. So for S-bus, this is the module to cycle space. You can view them as the hypersurface of inside this Riemannian manifold. So it's depicted in this picture. We have the interval here. Then we can consider all the consider the map from this interval to some hypersurface inside this Riemannian manifold. Right, so we can, and then the endpoints maps to 0. So in this case, we can obtain a sweepout. We consider all the set of all such maps. Then we can define the following min-max width W to be the infimum of a map phi inside this P, and then take the supremum. For each fixed phi, we can take the supremum of a point T inside the interval such that the area, like for example, in this picture, the area of this middle hypersurface is the maximal one. And then we can define this min-max value. Okay. So as you can imagine, if we put up the sweepout, then maybe the maximal one would behave differently. And then the idea is to try to find sigma n realizing the min-max width W here. And this can be done by using this Amgren-Peace min-max theory. So you need to prove that we can find the min-max sequence. We can find the sequence. If we have a sequence of phi, then we can find the sequence of phi of ti. And then the most important part is to show that the limit set is indeed a minimal hypersurface with a small singular set. Okay, let's skip the details here. And in fact, we can know more about the minimal hypersurfaces in a given closed Riemannian manifold. If the dimension n is between 2 and 6, then it is shown that there exist infinitely many minimal hypersurfaces. And currently, if the dimension is greater than 7, this also holds if we only consider generic metrics. So this when n equals 2, this is a conjecture proposed by Yao in 1982. So this was the result here was due to the development of my advisor Marcus and his collaborator, Engineer Navis. So in 2015, they showed that this is true if the Ricci curvature is positive. And later in 2017, Erie and they showed that for generic metrics, when dimension is between 2 and 6 Gauss conjecture holes, we can find infinitely many. And it was finalized by Antoine Song in 2018, showing that for any matrix with dimension between 2 and 6, we can find infinitely many. And myself, I showed that when the dimension is greater than no less than 7 for generic matrix, this also holds. And there are also some other development in the ungrain-piece min-max theory. There is a multiplicity one conjecture proposed by Marquis and Navis, and also some Morse index estimates, and so on. There are some contributors in these directions. Please forgive me if this is not a complete list. Forgive me if I didn't mention some authors on these directions. And also some in the min-max theory, there's also another setting proposed by Marco Guarco, which is the so-called Alenkine setting. This is the PDE version of the min-max theory. And they have also many mathematicians who worked on this setting and obtained some similar results in this direction. Say Marco Guarco, Pedro Gaspar, Otis Chodos, Christos Matulidis, Akushdeep, and so on. Yeah, this is not a complete list. Okay, so this is the existing result of minimal hypersurfaces. Now let's move to the singularities. A famous example was found by James Simons. It is the Simons cone. So this is a cone in the Euclidean space, in the 8-dimensional Euclidean space, denoted by C sub S here, whose section CS intersect with S7 is S3 cross S3. And it is shown that C sub S is actually an area minimizing cone. So it's not it's more than minimal. It's also area minimizing. And it's easy to see that in this picture, the only singular set is the origin here. So the dimension of the singular set is 0. So it's 7 minus 7. So this is the example if we consider minimal hypersurface inside the Euclidean space. And this is the first one with a non-trivial singular set. And in 1999, Nathan Smell showed that for any n no less than 7, he could construct a ambient manifold of dimension n plus 1, and also a homological area minimizer m sub n, such that the singular set m is exactly 2 points. In other words, in general, one can find a singular minimal hypersurface inside a Riemannian manifold, a closed Riemannian manifold. Recently, Liang Simon showed that in the Euclidean space, n plus 1 plus L for any closed subset in the third direction. So here n is no less than 7 and L is at least 1. Then K is inside 0 cross RL. One can construct a metric G, C infinity close to the Euclidean metric, and also a strictly stable minimal hypersurface sigma n plus L inside this Euclidean space with the new metric, this C infinity metric, such that the single set of sigma is exactly the K that we prescribed. So this also So these examples show that singularities are inevitable in general. One can even prescribe the singularities as complicated as one could imagine. So maybe the optimal thing that one can expect is that maybe you can put away singularities generically. In particular, is it possible that for any given Riemannian manifold, and with a C infinite generic metric G, there exists a smooth minimal hypersurface? Okay. So by the way, C infinite generic, the generic means that the complement of this generic set, this set should be nowhere dense. The countable union of nowhere dense subset. So this is in the bare generic in the bare sense. Okay, here is the singularities inside minimal hypersurface. So we can talk about some generic regularities to give the affirmative answer to this question in dimension 8. So from now on, we focus on the case when n plus 1 equals to 8. The other case, the higher dimensional cases are widely open. So we don't have any good result on there. So in 1993, Nathan Smell showed that if the homological class, 7-dimensional homological class of the ambient manifold is non-trivial, then for a generic metric G, there exists a smooth homological area minimizer sigma 7 inside the closed Riemannian manifold here. The proof of this theorem relies on the analysis of area minimizing cones with just one single point by Hart and Simon by their work in 1985. So here's the theorem proved by Hart and Simon. They show that because we know that now given area minimizing cone inside the Euclidean space, let's assume that E is one of the two components, E plus and E minus of the Euclidean space, removing the closure of this area minimizing cone. Then that we can find an oriented kinetic embedded real analytic minimizing hypersurface S with the distance as equals and the original set is equal to 1. So as one can see in this picture, the green part is the area minimizing cone C, and one of the leaf is S. This S is minimizing minimal hypersurface with the following property. The first one is that if we consider a ray emitting from the origin, then it should intersect with S at exactly 1 point and transversely. Secondly, the singular S is empty. And the third part is that third property of S is that S is a graph over C outside a large enough set B sub BR, where R depends on this cone. See here. And by the first property, we can dilate because we are in the Euclidean space, so we can using dilation, keeping the ambient manifold invariant, and S would generate a continuous family of minimal hypersurfaces, right? So we can have a foliation of E by S and its dilations. And the fourth property says that S is unique up to scaling, up to dilation. So in other words, if we can find another minimal hypersurface inside E, then it should be either S or some scaling of S. And with this analysis, so here the a key point is that the cone C here is more than minimal. It should be area minimizing. Then we can have this kind of foliation on the one side of the one side of this cone. In particular, if we have a one-sided area minimizing cone, then in the side where C minima is area minimizing, we can still have the same results, the same foliation, and the same uniqueness. So with this theorem, we can give a proof of Nathan's Smell, a rough proof. So if we start with an arbitrary metric G0 and also an area minimizer sigma 7, then a priori we don't know that whether sigma is smooth or not, but we can consider we can fix one single point inside P if it's non-empty. Using Hart and Simon, we can perturb it locally. In other words, we select a ball small enough such that in this ball that P is the only single set. Then we try to catenate sigma 7 minus this set, this open ball, and then also some scaling of the S that we've constructed in Hart and Simon theorem, some scaling of that, and then we will get some sigma tilde smooth. So maybe we can take a look at this picture. So in this picture, the green part is the original area minimizer sigma with two singular points. But by Hart and Simon, we know that we can find a smooth minimal hypersurface nearby, close enough, maybe C infinity close. Now we can add some neck region so that we can concatenate. The black part is the neck region. Then we can concatenate sigma and also the S part that we've constructed. Okay. Then the final step is to perturb the metric G0 to obtain G, such that the smooth guy sigma tilde is minimal. And we can show that if R sub P, the radius R sub P is chosen small enough for each P, and also the lambda is chosen small enough, then we can make sure that G is C infinity close to G0, arbitrarily small. So this is the proof of Nathan's Smell theorem. And recently, using a similar analysis of this Hart and Simon, and also some trick inside the min-map theory, Chodosh, Lukumovitz, Belaya, they show that for a generic metric, there exists a minimal hypersurface such that the Morse index of sigma and the number of the singular set is the sum of them should be at most 1. In particular, if the Ricci curvature is positive, then we know that no minimal hypersurface is stable. So in this case, the index of sigma should be always at least 1. In other words, the second term should be 0 all the time. So in this case, sigma is smooth. In other words, they show that if the Ricci curvature for geometric, if the Ricci curvature is positive, then the ambient manifold admits a smooth minimal hypersurface. And more recently, Zhihang Wang and I proved that the result by Choudhury-Shlikoumovich layer could be generalized to arbitrary measure. We don't need to assume that the Ricci curvature is positive. But for a generic metric, the ambient manifold would always admit a smooth minimal hypersurface. Okay, so the main difficulty in our theorem is the following. So we know that the Hart-Simon only works for area minimizing cones, but it doesn't work for stable but not area minimizing cones. In that case, the analysis of Hart and Simon is not correct. So we need some different perturbation because we know that using Hart-Simon analysis, we can do some local perturbation. But here we may need something like global perturbations. And okay. So now let's move to the main ingredients of the proof. Try to overcome the difficulty that I mentioned here. So the first one is the global perturbations. The following proposition was proved by my collaborator in his paper. He showed that inside an 8-dimensional Riemannian manifold, if we have a minimal hypersurface sigma, possibly with some single set, and also C infinity function f, and a sequence Cj tending to 0. If a priori, if we assume that in each Riemannian manifold with the following metric, which is just some conformal change of the original metric, if we can find the minimal hypersurface sigma j, and also the index of sigma j is exactly the same as the Morse index of sigma. Moreover, sigma j converges to sigma in the very full sense. Then we can show that there exists a single point P inside the single set sigma and some radius R sub P, such that for infinitely many J, the single set of sigma J intersecting with this ball is empty. So in other words, as one can see in this picture, if we're given a sigma and also a sequence of sigma J converging to this sigma, then we can find a single point P such that sigma J is smooth nearby. So we will see a smooth path in this ball. And by Schoen-Simon's regularity result, we also know that near the regular part, right, like here and here, if J is large enough, then sigma J is also smooth. So the only bad part would be the other single points inside sigma. And so a naive way to think of this proposition is try to do some induction argument. In other words, maybe we can start from minimal hypersurface inside some Riemannian manifold with some metric, say sigma, and then we use this argument to perturb sigma to obtain some sigma j with j large enough. And using this proposition, we know that near P there is no single set inside sigma j. Then maybe we only need to deal with the neighborhood of sigma, the neighborhood of another point, or maybe the other points of sigma. However, there are two issues for this induction arguments. The first one is that given a sigma, how can we show that we can find a sequence of sigma j converging to sigma? This is not always true. For example, even in the smooth case, This would be guaranteed if sigma is non-degenerate. If sigma is degenerate, then this might not be true. We might not be able to find such a sequence converging to sigma. And the second one is more subtle. So here we know that near P, sigma j has no single point. That's the good part. We may reduce one single point. But the problem is that maybe inside near another point, say P prime here, in this neighborhood, sigma j might have more than one single point. So in other words, along this sequence, when sigma j converges to sigma, there might be more than one single points converging to sigma. So maybe we will see a bunch of single points near this P prime, and then all of them converging to just multiple points converge to one point. So we might not be able, we could not do the induction on the number of the single points. We need a new invariant of sigma of a given minimal hypersurface instead of the number of single points. Okay. So these are the two other ingredients that we need in order to prove our main theorem. So in order to solve the first issue, we need the following uniqueness of min-max width realization. So here I need to mention that the sigma here, that sigma that we are considered is constructed from the Green-Peace min-max theory. So let's recall that in the Green-Peace min-max theory, we consider the set of all the three parts, and then the min-max width is the following min-max value. So if in the ideal case, if we can show that sigma is the unique one, realizing the width in some, with respect to some metric G, then if we put up the metric Gj, say, and then we consider a sequence of sigma j, each one of them realizing the width with respect to the Gj, then it's easy to see that sigma j indeed converges to sigma as long as Gj converges to G. Okay, so here the most important ingredient, a most important adjective is that the sigma should be unique in the given metric G. And we show that this is indeed true if under some technical assumptions. In other words, we can show that we can show this kind of unique realization. And our proof is inspired by Chodosh, Lyubomirsky, and Spalea. So we need to manipulate the three part, and then we also need to manipulate the magic to try to make sure that there exists only one min-max width realizer. And this is quite technical, so let me just skip this part. And then for the second issue, let's take a look at again. The second issue is to figure out a new invariant of sigma so that we can do the induction argument. So as I mentioned in the abstract, we need to try to figure out a clever way to count the single set. And here is the single points. So we define a new invariant called singular capacity. It is defined in the following triples. So which is sigma mg, where mg is the remaining manifold, possibly with some boundary, which is open, and sigma is a locally stable minimal hypersurface. we define the single capacity to be the following function on this tripod. To the image is just the non-negative integer and also infinity with the following properties. The first one is the finiteness. In other words, for any non-trivial stable minimal cone in the Euclidean space, the single capacity of this tripod should be at least one, but it's also finite. And the second one is the counting property, because the invariant, the single capacity is we are going to use this invariant to count the number of to count all the single points. So if there is no single point, then this one should be 0. Okay. And then if there are more than one, maybe if it's non-empty, then we'll consider the sum of all the single cone, the tangent cone. Here, at each single point, we do the blow up. And finally, the ambient manifold. If we do the blow up, the ambient manifold would be in the limit. The limiting ambient manifold would be the Euclidean space, and also the minimal hypersurface. The limiting minimal hypersurface would be a stable minimal cone inside the Euclidean space. Then we take the summation of all of them. So these two properties are natural if we would like to define some good invariant, right? And the next one is what we need in order to run the induction argument. Roughly speaking, we need the following upper semi-continuity. So suppose that we have a sequence of tripods sigma j and gj converging to sigma and g. Here we also need a technical assumption saying that sigma j is stable. But anyway, the main property is that the lim sup of the single capacities inside along this sequence should be no greater than the single capacity of sigma. So maybe one way to digest this upper semi-continuity is the following. So suppose that we are given minimal hypersurface sigma here. And if we perturb the metric to obtain some new minimal hypersurface sigma j, right? If in some, so as one can see in this picture, sigma has only one single point in this neighborhood, but sigma j has more than one. Maybe now we have 4. And then along the sequence as j goes to infinity, we'll see that these 4 single points converge to one point of the converge to this single point P inside the single set of sigma. So when we compute the single capacity of P, we need to take into account of all the single points of sigma j in this neighborhood. Okay, so maybe roughly speaking, we need to add all the single capacity of all of them, such that the single capacity of P should be no less than all the sum of all of them. So this is this upper semi-continuity. So when we define this invariant, we are not just considering the information of the single point itself, we will consider the information of all the nearby minimal hypersurface, all the single set of the minimal hypersurface nearby, all the sigma j here. And in our paper, we show that this, although the definition here is abstract, but we did construct such an invariant and show that the definition here is well defined using some induction argument. Okay, with these tools, we can prove our main theorem following the using the following strategy. So we can start from a Riemannian manifold with some given metric G, and also sigma inside this Riemannian manifold, uniquely realizing the width. Then we can put up G to obtain a sequence Gj and sigma J, which is also uniquely realizing the width with respect to Gj. The first step is to show that there exists a P inside sigma, such that a single set of sigma J intersect with the neighborhood of this P is empty. This is the first ingredient of this part. And using this proposition, we can show that the single capacity of sigma J is strictly less than the singular capacity of sigma due to the reduction of one single point near P. Right. Okay. And then we can repeat 2 and 3, such that because a priori we know that the single capacity, it's easy to see that the single capacity of sigma is a finite number. And then using the step 2 and step 3, we will decrease the single capacity strictly. And in the end, we'll see that the single capacity would be 0. So in this case, we'll obtain a new metric, maybe denoted by G tilde, and also a minimal hypersurface sigma tilde, such that the single capacity of this sigma tilde is 0. In our sigma tilde is smooth. So in summary, we can, starting from an arbitrary Riemannian manifold and also minimal hypersurface, we can do some perturbation, so C infinity closed, C infinity small, and such that we obtain a smooth minimal hypersurface in this ambient manifold with the new metric. The upshot is that we obtain the generic regularity of a minimal hypersurface inside 8-dimensional closed Riemannian manifold. Okay, and this is the end of story. Thank you.